In this lecture, we will be looking at exponential indeterminate forms. Recall L'Hopital's rule, which says if you have f and g differentiable functions, and you are looking at the limit as x goes to a of f of x over g of x, and direct evaluation of the limits in the numerator and in the denominator yield indeterminate form 0 over 0 or infinity over infinity, then we can apply the following rule, which says the limit as x goes to a of f of x over g of x is the limit as x goes to a of f prime of x over g prime of x. The key is this only works for these two indeterminate forms. But we see many different types of indeterminate forms, such as these exponential style indeterminate forms, like 0 to the 0, infinity to the 0, or 1 to the infinity. These are all indeterminate forms because they are not well defined. They result from a limiting expression like this, where you have the limit of a function in the base raised to a function in the exponent. So for example, if as x goes to a, f of x is approaching 0, and g of x is approaching 0, this limit could be many different things. It can be infinite, it can be finite. It will depend on how fast the base is approaching 0 compared to how fast the exponent is approaching 0. To deal with this type of indeterminate form, we use our friend, the natural log, because the natural log has a very nice property where exponentiation is changed to multiplication. So specifically, the natural log of a raised to the b can be written as b times the natural log of a. We apply the following algorithm to take advantage of this. And the key in turning exponentiation into multiplication is that it allows us to transform our limiting expression into something with multiplication, which we can then work with algebraically to try and get one of our two indeterminate forms that we can use L'Hopital's rule on. So our first step, just call the expression in the limit y. Then take the natural log of both sides. And when you take the natural log of f of x raised to the g of x, we're using this property of natural logs, where we can bring that g of x out front and multiply by natural log of f of x. We then concentrate on finding the limit of this expression here in 2. So the limit, L we'll call it, as x approaches a of this natural log of y. Once we finish computing that limit, we need only put it in the power of e, because the exponential, the natural exponential, e to the x, and natural log of x are inverse functions. We're using the fact that e to the ln of x is equal to x for any x. So let's see how this works in an example. The first step is to note what's happening with the base and what's happening with the exponent. We see that the base is going to infinity. So we know as x goes to infinity, natural log of x goes to infinity. We know that from the graph of natural log of x. One over x as x goes to infinity is approaching 0. So this is the infinity to the 0 indeterminate form. So let's use what we just saw on the previous slide and take the natural log of this expression. Even take e to the natural log of this expression. And this actually combines all of those steps into one. So I find this to be the most kind of natural way to do this, because by writing this as e to the natural log of that original expression, natural log of x raised to the 1 over x, we haven't changed anything. And again, because e and natural log are inverse functions, so nothing here has changed. We then are using a result from calculus that says this is equal to e raised to the limit as x goes to infinity of natural log of that expression, natural log of x to the 1 over x. And we can do that. This works because e to the x is a continuous function. So this is something that we learn can be done when we learn about continuity in single variable calculus. But this now allows us to concentrate on this limit here in the exponent. So this is then equal to e raised to the limit as x goes to infinity. We can use the property of natural log. So this is ln. Think of this as, here's your a, and that 1 over x is your b. So that b can come out front of the outer natural log term. So we have e raised to the limit as x goes to infinity of 1 over x times the natural log of x. We now want to write this in a manner that will help us use L'Hopital's rule. So we have e raised to the limit as x goes to infinity of natural log of x divided by x. And now let's see what would happen if we were to evaluate the limit of the top and the limit of the bottom. And we see that if we evaluate the limit of the top, natural log of x is going to infinity. And so natural log of x is also going to infinity. And of course, x itself is going to infinity. So we now have a limit expression that is fair game for L'Hopital's rule. So if we use L'Hopital's rule, this becomes e raised to the limit as x goes to infinity of derivative of the top divided by derivative of the bottom. So the derivative of the top will need chain rule. So the outer function, natural log, will have its derivative being 1 over the inner function times the derivative of the inner function, which is 1 over x. In the denominator, the derivative of x with respect to x is, of course, 1. So this becomes e to the limit as x goes to infinity of 1 over x times natural log of x. And here we have a denominator where you have two functions, x and natural log x, each going to infinity, being multiplied. So that denominator is going to infinity, which means the fraction itself is going to 0. And so we get e to the 0, or 1. I prefer to do these questions in this manner, personally. This algorithm is perfectly fine to use, but I find a very common mistake is people will get to step 3, get caught up in this limit computation, which tends to be the longer step, and then forget step 4 of putting that L that you compute in the power of e. Done this way, all those steps are collapsed into one, and things tend to work out a little bit more clearly. It's a little bit more writing because you have your e raised to the limit expression for each step, but you're much less likely to make that mistake of forgetting to put that limit that you find into the power of e at the end. And so this is really an illustration of how you use the natural log to change exponentiation into multiplication. And then that multiplication you rewrite as some kind of a division to get one of the two indeterminate forms for which L'Hopital's rule can be used.